Hello, Chem 1A. This is Chapter 6, Lecture Video 5, and we're going to be talking about how energy affects changes of physical state in this lecture video. So, the amount of energy that is required to change something's temperature, we can calculate using our equation that we learned earlier, Q is equal to mc delta T. However, to change a substance's physical state requires a different calculation because once we're even at the temperature that a physical state change occurs at, there's still an energy requirement to changing the physical state from one to another. For instance, a solid to a liquid takes energy to occur, right? And that energy is known as the heat of fusion. For instance, for water, the heat of fusion is 333 joules per gram of water that we're trying to change the physical state of. And for other substances, it'd be a different value. We need to put energy in, even if we're at 0 degrees Celsius, which is where the physical state change would occur for water, you're going to need to put energy in to get that solid water to the liquid physical state. And that value is known as the heat of fusion. The energy needed to convert a liquid to a gas is known as the heat of vaporization. At the same time, we have the opposite of these two values, right? Going from a liquid to a solid is known as the heat of solidification. I lost some letters there. Sorry, guys. Solidification. And these two are actually equal but opposite signs. So for instance, water, the heat of fusion, is equal to 333 joules per gram. The heat of solidification then is equal to negative 333 joules per gram. The opposite of the heat of condensation, in other words, a gas to a liquid, is known as the heat of condensation. And it, again, is going to have equal but opposite sign as delta H vaporization. And so this relationship, negative of each other, you should know that. So if I give you the heat of vaporization, you should be able to determine what the heat of condensation is because it's just the same value, just negative. The same thing is true of heat of fusion versus heat of solidification. Now, one of the interesting things about energy here is that when we change a substance from one temperature to another, and if we put energy in, we'll continue changing the temperature of that substance until we reach the boiling point or the melting point of the substance. For instance, at 0 degrees Celsius, if I put 500 kilojoules of energy in, my temperature of this iron block will go up to 557 Celsius. It won't stop there. If I keep adding more energy, it'll keep going up in temp, right? But when I hit 0 degrees Celsius for water, if I add 500 kilojoules of energy, the water's temperature, it stays the same. What that energy is now being used to do is, instead of changing temperature, we are breaking apart the ice crystal into the liquid state. And that energy is what is being used there. Instead of changing temperature, we're now changing physical state with that energy. So once we hit a boiling point or a melting point, our temperature will stop changing until all of the substance has changed to the new physical state. This creates an interesting calculation. Let's say I want to know, for instance, how much energy is needed to do something, right? Let's say convert some ice, let's do black, to steam, right? Let's say I had 50 grams of ice and I want to get 50 grams of gaseous water, of steam. Well, at, let's say, 200 degrees Celsius. And this was initially at -50. Well, that's an interesting calculation. It involves actually 5 different steps, right? So the first step, we'll do different colors here, is converting, and this is Q1, this is converting the 50 grams of ice at -50 to 0 degrees Celsius. That's our first Q. Our next Q, Q2, is changing our state from solid to liquid. And how much energy does that require? That is going to be our heat of fusion. Next, we're going to raise the temperature of our 50 grams of 0 degree water to 100 degrees Celsius, because that's the boiling point of water. And that's just a Q is equal to MC delta T calculation. Then finally, not finally, but then next we're going to, in Q4, change our physical state from liquid to gas. And this is going to involve our heat of vaporization. Then finally, we are going to, for Q5, raise the temperature from 100 degrees Celsius to 200 degrees Celsius. And so each one of these Q's we have to calculate, and then we'd have to add together to calculate how much energy this would require. This graph is super valuable. It's called a heating curve. And notice where the flat parts are. This is the heating curve specifically of water. The first flat part is at 0 degrees Celsius. That is the melting point of water. And the second flat part is at 100 degrees Celsius. That is the boiling point of water. And this is always where these flat spots in the heating curve occur. Wherever the boiling point and the melting point are, the rest of the lines are going to be diagonals. So let's talk about how to do this type of calculation. All right, so let's say, right, we have 500 grams of water. We want to warm it from -50 degrees Celsius to 200. Obviously, hopefully, we know that at -50, it's in the solid state. And at 200, we hopefully know water is in the gaseous state. So we have some steps here for this calculation. The first step is to warm the ice from -50 degrees Celsius to 0 degrees Celsius. In this step, we're not changing the physical state of the water. So we're going to use Q is equal to MC delta T. Now C here has a different value. It's not 4.184 because ice, solid water, has a different Q than liquid water. But otherwise, it's the same idea, right? Our 500 grams here, that's our M. Our delta T is going to be T final is 0 and T initial is -50. And we can look up the specific heat. Next, we need to melt the ice at 0 degrees Celsius. In this step, we're not changing temperature. We're just changing from solid to liquid. And this involves the heat of fusion. What we do is we take the heat of fusion, which often has units of joules per gram, and we multiply by mass, right, in grams. Grams will cancel, we'll be left with the amount of energy, joules, that we need for this conversion to occur. So in this case, this is our M here is our 500 grams. Heat of fusion would be given to you in the problem. Next, we want to go from 0 degrees Celsius to 100 degrees Celsius. This again is a change in temperature, so we're going to use Q is equal to MC delta T again. But in this case, the C is now for liquid water because we're in the liquid state. Our delta T is final is going to be 100. Our initial is going to be 0. Our mass is still 500 grams. And so we can solve for Q here. Next, we need to change from the liquid state to the gaseous state. And this involves our heat of vaporization. The calculation is almost identical to step 2. It's just we're using a different heat of value because we're doing a different physical state change. But usually, again, these are in either joules per gram. Most often they're in joules per gram, and the heat of vaporization will be given. You just need to multiply it by the grams. Then we need to heat the steam to 200. So now we're in the gaseous state. We're at 100 degrees Celsius. We want to go to 200 degrees Celsius. Again, we're changing temperature, so we're going to use Q is equal to MC delta T. This is now the specific heat for gaseous water, and we're almost done. The last step, we want the total quantity of heat. We need to add all of the heat values that we calculate in these 5 steps together to get our amount of heat that would need to be absorbed. We could do this in opposite order for released if we were going from a high temperature to a low temperature. So context in our problems is very important, right? If you're going from, instead, this number is over here and this number is over here, you're going from 200 to negative 50. All of your Q values should end up being negative in that scenario. You won't be using fusion and vaporization because you'll be condensing and solidifying instead of melting and vaporizing. So there are some small differences. So let's do an example problem. So we have 35 grams of water in the gaseous state at 120 degrees Celsius, and we want to get it to the solid state at negative degrees Celsius. We're told the enthalpy, or this is just a fancy word for heat, of vaporization is 2,256 joules per gram, and the heat of fusion, or enthalpy of fusion, is 333 joules per gram. So if we think about this graph that we have here, we have this type of graph, and right now we're all the way up here, right, at 120 degrees Celsius. And the first step that we need to go to is going to be here. We need to cool this down until we hit 100 degrees Celsius. So our first step is go from 120 to 100. Why 100? Well, that's the boiling point of water. If this was a different substance, we'd be dropping the temperature until we got to the boiling point of that substance, whatever it is. And I expect you to know what the boiling point and freezing point of water is, in Celsius at least. So here's my first Q calculation. I'm going to call it Q1, and it's going to be equal to my mass, 35 grams, times my specific heat. We're in the gaseous state, so that's 1.86 joules grams Celsius, as we can see here. And then I'm going to multiply this by delta T, which T final is 100 degrees Celsius, T initial is 120 degrees Celsius. This is going to give me negative 1302 joules of energy. After this, now I need to convert from my gaseous state to my liquid state. I'm going from gas here to liquid there. Well, Q2 then is going to be equal to the mass times, how do we go from gas to liquid? That's condensation. So heat of condensation, I'm just going to abbreviate it, con, times my mass. Well, I don't have the heat of condensation, I have the heat of vaporization. Well, remember, we talked about this earlier. Heat of condensation is equal to the negative heat of vaporization. I'm just going to say vapor. Which means I do have the condensation value. It's just negative 2,256 joules per gram. So in other words, Q2 is equal to 35 grams times negative 2,256 joules per gram. This gives me negative, as Q2, negative 78,960 joules. All right, so the next step is going from that temperature at 100 degrees Celsius to 0 degrees Celsius, because 0 is the freezing point now of my water. So Q3 has to be from basically going from 100 degrees Celsius to 0 degrees Celsius. And now we're in the liquid state, so we're going to use the liquid specific heat. So 35 grams times my specific heat of liquid water times delta T, which T final is 0, minus T initial, which is 100, this is going to get negative 14,644 joules of energy. Now I know technically all these should have only 2 sig figs, but I'm just going to kind of ignore it for this problem, to be honest. And then the next step, Q4, is equal to going from really the liquid state to the solid state. So Q4 is going to be equal to my mass times my delta H, or my heat of solidification. Now I don't have that value given to me in the problem, but I do have the fusion value, and just like with condensation and vaporization, the heat of solidification is going to be equal to negative heat of fusion, which means this is equal to negative 333 joules per gram. So Q4 then is going to be equal to 35 grams times negative 333 joules per gram. This will give me negative 11,655 joules of energy. The last step, right? We went there, then now we're here. We need to go to here, which is negative 10 degrees Celsius. So Q5, now we're in the solid state, is going from 0 degrees Celsius to negative 10 degrees Celsius. And so my Q5 is going to be equal to 35 grams times the specific heat of ice, which is 2.06 joules grams Celsius, times, well, my final temperature is negative 10 degrees Celsius, and my initial temperature is 0 degrees Celsius, so this is just negative 10 is delta T. And if we calculate that out, we get negative 721 joules. Okay, so at this point we have all 5 Qs. I know I have this value here, this value here, this value here, this value here, and this value here, and I need to add these all together. So Q total is going to be equal to negative 1302 plus negative 78,960 plus negative 14,644 plus negative 11,655 plus negative 721. And this all equals my total amount of energy that would be required. At the end of the day, this gives me negative, all right, I'm going to just throw it up here. This gives me negative 107,282 joules of energy. At the end of the day, if we round this to effectively 2 sig figs, it'd be 110,000. Negative 110,000 kilojoules of energy would be required to do this. And so this is a typical problem in this scenario. One thing you got to be careful with is assuming you're doing all 5 steps. If I had said that we're going to, 50 degrees Celsius, well, we have 2 less steps in our calculation because we're not in the solid state, we're in the liquid state, right? And so you got to really carefully read the problem. You might not have to do all 5 steps, you might have to do a couple. But yeah, if you have any questions, as always, please feel free to contact me.